So, ladies and gentlemen, good morning. Again, sorry for the delay. I really had a hard morning, but it's over. We can relax, and we still have enough time to talk about quantum transport. Again, as almost every lecture, we have a topic change. However, this time it is just a combination of two topics we have treated previously in lecture number 5, when we talk about Coulomb blockade, and in lecture number 6, I believe, when we talk about Josephson effect. So we just combine these two and consider the structures where superconductivity and accompanied Josephson effect is combined with Coulomb blockade. Why it is so special for us, why I put so much stress on this. Eventually, this combination enables us artificial homemade quantum mechanics, which is currently, with much success, is used in quantum technologies in quantum computing. We don't go immediately to quantum computing, rather we will discuss today physics, which enables us, we understand why this combination actually will give us necessary technological tools to create, to manipulate, to process quantum states which are made at micrometer scale. Why it is important? Well, we have natural quantum systems, atoms, but we have hard time in many cases to control them, to make it to behave in the way we like. We have a difficulty to engineer the atoms. It is much simpler, the systems which we'll describe now. What is the essence and short summary of what I'm going to say? Well, we will consider Josephson effect, and so we have to make superconducting the islands where charge is stored and Coulomb blockade is manifested. And we are going to quantize the system. We are going to quantize it just from scratch, and I will explain you how one can do such things. Our main conclusion is that superconducting phase, characterized in Josephson junction, and charge, which can be stored in an island, are canonically conjugated variables, very much like momentum and coordinate in quantum mechanics of single particle. That's a key point. Starting from this, one can already readily make all quantum applications. Right. It is essential that there's some periodicity in phase, which corresponds to phase change by 2 pi, and charge quantization periodicity in charge, and that needs to be discussed neatly. Eventually, there are 2 answers corresponding to 2 different systems. We will look at the limits where one of these 2 conjugated variables is well defined and other not. We will look at physics of single junction, at microscopic quantum tunneling in Josephson systems. In the end, I will talk a little bit about the systems of big number of Josephson junctions, some kind of artificial matter, which one can make from Josephson junctions, which are called arrays, and a bit about vortices in these arrays. Good. Everything is clear, outline is clear. Let me just, that's not what I want. This is the early. Right. Let me explain why do we need this combination. Why from all variety of tools which is provided by modern nanotechnologies, we pick up this one. Well, Coulomb blockade by itself can be already seen as a sort of quantization. Charge is quantized. But it's not quantum quantization, right? There are states of different charge, so pretty well quantized, but these states are not unique quantum states. Why is it so? Because if one takes normal metal island with small level spacing, one can easily create electron hole pairs in this island, which will belong to the same charge and state, but it will be a distinct quantum state. And we know if we have many states corresponding to the same marker, to the same physical value, then we are surely in classical. So Coulomb blockade by taken alone cannot work because it's not coherent to many states. What is essential element of superconductivity? It brings coherence. It does it in two ways. First of all, it already in its macroscopic state has a quantum element, has superconducting phase, owing to gauge or to breaking of gauge invariance. Second, there are superconductors and superconductors. We have discussed it thoroughly. Most superconductors have gap in energy spectrum, right? And this gap helps a lot. If there is a gap, you cannot readily create electron hole pairs with small energies. So, in this case, you really have unique quantum state. To give an overview, there are superconductors which do not have the gap. Superconductors with magnetic field, superconductors of strange symmetries of other parameters. Usually they're not suitable for quantum technologies as we know it. Right, so if we combine Coulomb blockade and Josephson effect, we will have quantum states. Roughly, there's association of a single quantum state with each charge state. Okay, it's a bit more complex, but we will discuss it. Right. Why do I call it homemade quantum mechanics? A point which you perhaps missed, that one can work at home at sub-micron scale. Perhaps just like many sensational news just can come and go. But perhaps you have heard about the guys who wrote, for instance, Holy Quran on a rice grain. Have you heard about this? It's possible. And eventually, once I read how people do this, what you need is investment around $200, perhaps 200 euro. You need a decent microscope, and you need good grips, and just several grains of sand. People take a grain of sand with a grip, concentrate on a field of put it under microscope, also with some other grips. And really you can, with your own hand, work at submicron scale. Submicron scale, 100 nanometers, is also something which is typical for devices, Josephson junctions, and Coulomb blockade islands, which are manufactured from metals. And that is quite sensational, right? If you think about this. Because we have single quantum states, which are usually observed in single atoms. But the total number of atoms in your device is at least several billions. And all these atoms, by some magics, just work as a single quantum state. Yet 40 years ago, there were people who doubted this, and they told us it is something wrong with quantum mechanics. We know it couldn't be that so many atoms are orchestrated in such a way. Well, nevertheless, it's a fact. It has been experimentally proved around that time. Indeed, very big systems can behave as single quantum states, as single atoms. Okay, that was a kind of general philosophy or whatever sensation. All the stuff. Any questions about this? Then we can go to details. Right. So we consider superconducting island. Eventually, it is the same device which we have considered in the context of Coulomb blockade. There is an island to store electrons. The number of electrons should change so that the island is in contact with some lead, a source of extra charge. Both lead and island are superconducting. That's why the junction which connects it to is a Josephson junction. Good. And there is also a gate, not to forget, gate is essential, and this gate shifts the potential of the island with respect to the lead and tries to put more or less electrons into the side. Right. To comprehend, to model what is going on, we can do quickly in a very simple fashion. But then we have to think, but that's usual price which we pay for fast solutions. Right? We decide something, then we have to think about what we have. We have Josephson energy due to Josephson junction. And we have learned a week ago that this is a function of superconducting phase, cosine function, which corresponds to sinusoidal current. Good, Josephson's energy. And from the island, we inherit Coulomb energy. As you remember, that expression is defined for discrete number of charges. And this discrete number of charges can be, its optimal value can be shifted by changing gate voltage. So to remind you, we had a set of parabolas for each n versus this guy, which is usually called Q, induced charge. We have a series of parabolas. I will show these parabolas in more details. Good, so Josephson energy and Coulomb energy, which actually depend, as we see from these expressions, on two different variables, phase and charge, or number of electrons. I would consider even number of extra charges. For most of this, I don't want to discuss now why, but perhaps you can answer this question. Yes?
Because the superconducting gap is bigger than the charging energy, so you don't get excitation.
Yes, you're right. Or in another formulation, this is Josephson junction. It does not transfer single particle excitations, which are absent at low energies. It transfers pairs. It means that the charge of the island would only change by 2 or 4 or any even number. Good. Let us try to understand the link between these variables, phase and charge. And doing so, we will run a procedure which is called quantization. Eventually, for those who attend the course of advanced quantum mechanics, this is precisely the same procedure which we have implemented for quantization of oscillators, quantum oscillators. And here we just, being engineers, we just apply it not to abstract oscillators, but to the system in hand. Right, what is the procedure? It's, again, it's not something which comes from the blue sky, it's something which we do, which we engineer. So first of all, we replace the classical variables by operators. That doesn't help much because we don't know what is the effect of putting the operators in different order. We have to fix that, and this fix is provided by postulate of commutation relations between these operators. Then, essentially, it's a gas of commutation relations. It is a gas which can be checked. What is a check? One derives quantum equations of motion. Energy amounts to Hamiltonian. commutating any operator with Hamiltonian, we have Heisenberg equations of motion. And these equations of motion should correspond to classical equations of motion. Good, let's do this. I want to make little simplifications with the Josephson energy and with Coulomb energy. Yeah, eventually, if I am frank, it reduces the system to harmonic oscillator. But let me do it, let me not stress this. Sure, cosine phi in Josephson energy. What is this? It's a function like this. Zeros here, minus cosine phi. So it has a minimum near zero, and perhaps it's a good idea to look at small deviations from this minimum. So we expand cosine phi, keeping leading term contributions in superconducting phase. And as to Coulomb energy, I just skip the term with gate voltage. That's what we end up with. That is going to be our Hamiltonian. Right, so let us understand classical equations of motion. We don't have to do any regular procedure, we don't have to derive any Lagrangians or whatever. We could just proceed with what we know from first year physics. Charge in the island, its time derivative must be the current, right? The current for this choice is proportional to phi. One equation. Second equation is a Josephson relation. Time derivative of phase is proportional to voltage. And one also needs relation between charge and voltage. Okay, that's definition of capacitance. Right? This is a system of equations. I just want to rewrite it in quantum notations, these classical equations. That's what I substitute to make it quantum. Good. So I substitute all this and I can rewrite these two equations in a nice symmetric form. So derivative of number of particles is proportional to phase, derivative of phase is proportional to number of particles. And the coefficients are two energies, charging energy and Josephson energy. Fine, all right, so now we want to choose to guess the quantization postulate. And let me really present it as a problem with a tunable parameter. So I just say the commutator of these two operators is a constant, which I don't know yet. All right? Good. Then I can use these commutation relations to commute Hamiltonian with these two operators and to get a resulting equation of motion from Heisenberg dynamics. From that, I shall conclude that alpha is nothing but minus 2 pi. So it's constant operator, and that immediately reminds us the relation between momentum and coordinate for a single particle quantum mechanics. So we can immediately use all experience with these particles, all tool set which we have to describe single particles. Right. This is a bit arbitrary choice, but let us treat phase as a coordinate. The number of particles charge must be something like momentum. So how momentum would be represented in representation or in phase representation, in coordinate representation? Well, that we know, it's gonna be derivative with respect to phase. Right. I could write similar relation for the phase. So in representation, which corresponds to in charge representation, the phase would be derivative of with respect to n. But that's not what I want. Because if I get the original expression for charge and energy, I don't have phase explicitly. I have cosine, which is made of two exponents. And that exponent, wonder if you know that, perhaps somebody told you in your quantum course. This is eventually a shift operator in charge space. What you might know is that if I again talking about analogy between single particle quantum mechanics, if I take this operator, exponent of momentum or exponent of derivative, and apply it to wave function which depends on x, Coulomb circle can get the result.
Five x minus alpha.
You just computed in your head, or you've heard about this?
Well, you said it was a shift operator. So.
Okay. This is a shift operator indeed. One can prove this formula by kind of expanding in alpha and looking at all terms with derivatives which arise from this expression. Good. What does it mean for us? For us, it means rather physical conclusion. Actually, pretty nice one. This exponent, phi, just adds 2 electrons to any quantum state. That's what I wrote here. So that's initial wave function, that's final wave function. So it just shifts the number of electrons by 2. Exponent minus I phi does the opposite, because the product of these two exponents is 1. So it shifts n by -2. So if you shift it by +2 -2, you got the same, and that corresponds to the fact that the product of two exponents is 1. Fine. So we have quantized our system in fact. What would be the next step? Next step is to do something practical and write Schrödinger equation, which will describe quantum states in this system. How we can build up this Schrödinger equation? Right, it's the Hamiltonian. The Hamiltonian can be written in different representation. So here I choose two opposite representations, charge representation. Then look at Josephson of energy comes as a potential. Potential is coordinate dependent function and phi is a sort of coordinate now. H2 charge and energy, it becomes a sort of kinetic energy of a particle. It has precisely the same form. And that addition due to the gate, it comes as a magnetic field affecting the phase of this particle. Good, that we do in phase representation. What is in charge representation? In that case, Coulomb energy is diagonal. It's a diagonal operator, so it just amounts to a function which depends on n. And Josephson energy, as promised, shifts wave function by plus or -1, which corresponds to pair transfer in two opposite directions, from the island and to the island. Very good, it seems like we have done. But there is a funny question which usually physicists do not want to pay attention to, because usually you can guess these mathematical details from usually for physicists the choice which mathematicians have to think hard of. This choice is obvious, but not in our case. It's an interesting answer. And what is the question? The question is, what are boundary conditions for these equations? Let's talk about phase representation. We could look at this equation and solve it for functions which are periodic in phi. Right, so this is this potential, and the wave function is just the same at -pi and pi. Can you imagine this? Nobody has problem to imagine this? I had. For me, the following consideration has helped. Let us just consider a cylinder in gravitational field. Just we make it from wood, and let us make a trajectory for particles, which is a slanted cross section of this cylinder. So I have a plane, I have a cross section. That's how does it look like. If you recall trigonometrical relations, you understand that this is a realization of cosine potential. If one treats this coordinate as a phase, that's going to be precisely this. Fine, but here it is obvious that wave function is periodic. It has to be the same at plus pi and minus pi. Yeah, but who told you so? The same equation can be really implemented for the case when wave function is not periodic. In fact, it looks like a particle equation for a particle in periodic potential. And we know a lot about this equation from solid state physics. We know that solutions are Bloch waves and they don't have to be periodic. So there's a question for us, but from two possibilities we have to choose. And let us address this question after, let's see, after 5 minutes break. Very good. So we have this integration. You still doubt about boundary condition. And usually we can make a very physical choice, but not in this case. And the trick is that eventually this choice of two boundary conditions describe two different systems. Let me argue why each choice describes what it's supposed to describe. First of all, let us concentrate on wave function which is periodic in phase, like this. Let us neglect charge and Josephson energy for simplicity. Then the solutions to these equations will be plane waves, but these plane waves are subject to periodical condition. So, like it usually happens, wave vector of these plane waves is quantized. It is quantized and it gives rise to a series of discrete states. And if you look at the states, we understand that this letter n is nothing but charge, number of particles corresponding to a given state. Fine. It means that this equation describes a system where charge is quantized. And as we have learned, it means that there has to be an island where this charge can be stored. Let us look at another variation of boundary condition. Let the phase to change from minus infinity to plus infinity. In this case, if we skip Josephson energy, the solutions to this equation will be so-called Bloch states, which are known from solid state physics. So in fact, it will be also plane waves, but with a continuous wave vector. Right. So it means that the charge is not quantized. It means that it's no island. And this system of equations eventually describes a single junction, single Josephson junction between two leads, where we have Josephson link and also some capacitance between these two leads. So equations are identical, but boundary conditions, which we said, are different, and we can describe two distinct systems. Okay, we have sorted this out. Let me concentrate on the island, and let me outline two limits to understand more about the resulting spectrum. What did I do? Okay, better. Let us first consider, okay, we have two parameters to compare with each other. Charging energy and Josephson energy, two constants. And let me first assume that charging energy is most important one. So then in zero approximation, I can just forget about Josephson energy. Then I just passed and copy, cut and passed, the picture I have already shown to you, picture of charge states at different number of discrete particles versus gate voltage. And as we remember, there is a ground state, there is a first excited state, and third excited state. I put it in different colors. They are obtained by connecting the pieces of parabola, so the same height. Energies of all these states are periodic in charge. And okay, that's an answer which we can understand, but it's, yeah, frankly, it's pretty boring. Fine. Let us look at it with some precision, with some attention. Let us concentrate on the points where two charged states intersect and are at the same height. Those are called degeneracy points. Right. And in this situation, even small Josephson energy makes a qualitative difference. It will make the states quantum superpositions of one another. Will provide quantum mixing between the two. Simultaneously, it will open a gap in the spectrum. It will the levels will avoid each other. They will repel each other closer to intersection point. That's what I put in words. Perhaps it's good if you could, whatever, tolerate a small piece of algebra. Shall we? Okay. So it is, at first start, it's pretty classical system, but in fact it is quantum. Let me concentrate on the closer vicinity of these two states, then I immediately got an idea that perhaps only these two states are important for quantum mechanics, which means that the Hamiltonian, which I want to write, is a 2 by 2 matrix. All right, so now let me fill in this 2 by 2 matrix. Let me work in charge representation. There are two diagonal elements, here and here, will correspond to the energies of the charging states. Fine. Let me introduce a parameter which shows the deviation from this crossing point. I will call it epsilon, just for a change. Then I see if levels cross. Here, one is proportional to this epsilon, another one is minus epsilon. Right? They go like this. Fine. Now I want to describe Josephson energy. I want to account for possibility of quantum transitions between these two states. Could you tell me what I have to do?
Calculate the matrix elements.
Calculation is barred. I have to do something simple with this matrix. So what do I have to do with this matrix? So there are transitions between these two states, which means there must be some non-diagonal element. This non-diagonal element happens to be, if one can calculate this, and this is simpler calculation because, it follows from the form of Josephson energy we wrote. This is just e.g. eventually over 2. Very important. Good, so we have 2 by 2 matrix. We solve it for energies. There are energies plus minus, and both they have this hyperparallel. Right, something like epsilon squared plus e.g. over 2 squared. That's what I have in this plot. And if one computes eigenfunctions corresponding to these eigenvalues, one obtains superpositions of two charge states. So even at this limit, one can make quantum system, and eventually a very convenient one, which will have only two states, kind of elementary quantum system, spin or qubit. Fine. So it was a case where charge was well-defined quantity, again, except this isolated crossing points. Let us go to opposite limit. Let us consider the case when Josephson energy is very big. Right. The picture has changed quite a bit. So it's again dependence on gate voltage, but for low levels, as we see, there is no dependence. Well, how to understand this? Let's draw a potential corresponding to Josephson energy, quite a high potential, which has energy scale Ej. Right. Charging energy is small. It means that quantum fluctuations in this potential are small. Fluctuations are small. Low energy states are concentrated. Let me put it in different color. Close to to the bottom of the potential. What is A? As we know, any minimum can be approximated with Taylor expansion, can be approximated as x squared. So if effectively we have a harmonic oscillator, right? So we have a system of almost equidistant levels, but if we increase the energy, the distance between these levels will also change. Fine. And these states are localized. The electrons, the particle, when it moves within the state, is reflected from the walls. It never makes a full circle. Let's go to higher energies, somewhere here. And at these high energies, we could even neglect this potential. We have only kinetic energy, which brings us again to the picture of charging states. And indeed, here at high energies, we already see something like crossing parabolas with avoided crossing. So that sets the spectrum, that explains the spectrum in this case. So in fact, going a bit ahead of the program, the most popular organization of qubits, quantum bits now, corresponds to superconducting islets with very pretty big EG, so that in fact they use the levels of the oscillator. One cannot quantum compute with oscillator. They also have some residual non-linearity of these levels, which they use for quantum computation. Good. So two limits, and let me. Oh, am I ahead of schedule? That's interesting. Let me tell you about a couple of differences. Or are there other questions? Because what I said, these two transparencies, perhaps it's not that obvious, are kind of important, fundamental. Yeah.
Yeah, I don't absolutely get this last slide explanation why for the low levels we have flat and equal spacing levels, and then we have this curvature for higher.
Okay. So again, it's this picture with a potential. Let me put the axis. This is the axis of phi. If Josephson energy dominates, phi is a relatively good variable. So in first approximation, for low energy states, phi would be just at the bottom. Yeah, but it's not interesting. We want to have some excitation, some states. Right. How we can do this? Charging energy is small, so we expect that quantum fluctuation of this phase is still small, at least for low line levels. If it is small, the particle does not go too far from the potential minimum. If it does not go too far, we can, as we did at the beginning of this lecture, replace cosine with phi squared. That's a constant we don't have to take into account. This is potential of harmonic oscillator. So we have kinetic energy in this oscillator, which is charging energy, and potential energy, which is Josephson energy. Fine, we quantize this oscillator, and we have almost equidistant levels. One can estimate the separation of the levels, which is frequency of this oscillator. And as I put here, it's a, how would I say, geometrical mean. Does it sound for you?
Mm-hmm.
Geometrical mean of charge and energy and Josephson energy. Right. Now we understand low line excitations. We go farther in energy. And if we go farther in energy, okay, we see that the potential is not already parabolic. There are substantial deviations in the shape of this potential. Consequently, the levels are not the levels of oscillator, they are not equidistant anymore. Their positions deviate from those of oscillators. What does it mean? That the oscillator became a nonlinear oscillator. And this is a property which is used in modern qubits, so-called transmon qubits. Fine. All right. Those are energies of the levels which are, let me quickly rewrite it, which are localized in this potential. So if the energy is smaller than the height of this potential, smaller than Eg, a particle would just oscillate between the walls of this potential. So it will never make a round, will never cross this pi minus pi boundary. Good. If it doesn't make a round, it's not sensitive to the gate charge. But we can easily comprehend the situation when this energy is much higher than the energy of Josephson, right? So anyway, if you increase energy, sooner or later, charging energy, which is proportional to n squared, will become bigger than Josephson energy. What is a picture we can use there? It is a picture which we have here, charge and states. So at sufficiently high energy, these levels will resemble charge and states. Lane waves in phase space. And they will depend on gate voltage, as you see here, and as it is shown here. All right, that's what I can tell. Ask questions. Good. Let me describe. I could make it experimental, but the experimental details in this experiment were a bit too complex to describe. It's not physical complexity. It's more about the measurement procedure and electronics they put into it. So I just concentrate on some sketch of what is going on. That was, I mentioned at the beginning of this lecture that some people actually doubted that quantum mechanics can occur at micrometer scale. They thought, oh, perhaps we don't quite understand quantum mechanics, perhaps there are some effects which we are not aware of, would play a role at this distance. No, that is that's too hard to imagine that a big system would behave as a single quantum state. So this experiment was the first proof of this concept. So it's called microscopic quantum tunneling. And that was just single Josephson junction. Let me recall what we discussed in the context of classical single Josephson junction. That was a Washburn potential. So what are the components? It's a Josephson energy, which is periodic function of phase, and the current, bias current, which provides a finite slope to this potential. Good, that's classical potential. Let us put a quantum particle into this potential for a current which does not exceed critical current. Okay, it will stuck in the bottom of the well. But if it is quantum mechanical, the particle is delocalized, it explores the whole space around this minimum, and in particular, it can tunnel through this potential barrier. All right, it can tunnel, and let us recall Josephson collection. Let us understand what will be manifestation of this current. I mean us. I mean you. Please recall Josephson relation and tell me what will be the manifestation of this jump. What is Josephson relation which we use? It is a relation between time derivative of the phase and
current.
Okay, let's start from very beginning. We still have half an hour. Almost voltage. So that was derived by this young, wild genius, Professor Josephson, in the age of 24, I believe. Just looking at the concept of gauge invariance, he figured out that applying voltage to Josephson junction would set phase into motion, and this motion, the speed of this motion, is just proportional to voltage. That's what we also use to derive equations for Josephson circuits. Good. Let's apply it here. So there's a particle tunneling from one well to another well. What would be manifestation of this?
Voltage difference.
Okay, for a single particle, it would be just voltage spike. If you have many things going on, if it tunnels many times, indeed you would have some voltage in average. And that's roughly how do they measure it. Biggest challenge was the following. We did mention here in our discussions the effects of finite temperature. If temperature is finite, even classical particle, as you know, as you have feeling for, can overcome this barrier, just picking up by chance energy from temperature fluctuations. So most experimental work went into excluding this temperature effect. Apparently you need low temperatures, but you need low temperatures anyway for superconductivity. Good, then whatever quantum question or training for future exam, which will be multiple choice questions. That experiment was made in a certain year, and there are three possible answers, A, B, C. What you would vote for? What would be your choice? Okay, let's make an example. Who has A? Who has B? Who has C? Okay, B wins, and it's again, I would say, a reasonably Dutch way to be moderate, to be in the middle. Let me tell a little bit about history, but how did it go on? 64 was a year close to discovery of Josephson, to first experiments with Josephson junction. So it could, but it would be very unlikely that first experiment with Josephson junctions would be quantum mechanics. 2005, it's too close to modern times. By 2005, we have had already qubits working even in this building. So it has to be somewhere in the middle, and it was in 1985. That is when I got my PhD eventually. Fine. Quantum tunneling. First experiment which showed that indeed that's possible, homemade quantum mechanics is possible. And let me talk about a detail which I have mentioned in the beginning, but still have to elaborate it. You kind of guess correctly what is the reason for that. We talk about even number of electrons, and that is to a strange property, which also one of the things which people had a difficulty to believe. Let us consider a superconducting island. So its energy, so there are some Cooper pairs at zero energy. One would not pay much energy to create a Cooper pair, but if one would put a single particle, a quasi-particle, doesn't matter if it's charge plus one or minus one, it would necessarily go into this excited states above the gap. And it will be separated by energy, at least the gap. Good. So what will happen if we have another particle, if we add another particle?
We don't have to pay the gap energy, only the charging energy.
Precisely. So if we add another particle, one doesn't have to pay this energy, one can add just a Cooper pair, and that causes zero energy. So that means that energy of a superconducting island depends on the parity of number of charges there. It is smaller for even numbers, it is larger for odd numbers. So here I sketched parabolas for even and odd numbers. So the scale of parabolas, as we know, is charging energy. The scale of the shift is delta. So if delta is smaller than charging energy, then we have both parities, and that's eventually, how to say, inconvenient. Yeah, inconvenient is polite word. Eventually it's very inconvenient for applications because your system jumps between two possible parities. You never know which state it is on. So for applications, it's convenient to make a choice where the gap is larger than charging energy. One of these things is not correct. If the gap is larger than charging energy, then we can just forget about even states. About odd states, those with high energy. So it's the essence of parity effect that kind of justifies what we have assumed from the very beginning. We can talk about a array of Josephson junctions. Let me make a short philosophical introduction. If you just follow textbooks, the history of physics might seem as perhaps difficult, but rather continuous escalation, continuous hike from no knowledge to more knowledge to new summits. But if one really looks at details, it's not always step by step road. It happens frequently that people get inspired, they take a challenging road to unknown, they try their best, but for some reason they stop. They have to turn back. And continue along main road. Not what is good, that main road still persists, still goes up, and perhaps at some stage one can reach from another direction the place which one was not able to reach directly. So what does it mean in the context of Josephson junction? It became obvious theoretically from very beginning that interesting things will happen if you combine many islands together. Say what would be fast analogy, each Coulomb island, one can make a sort of artificial atom out of that. If you stick many atoms together, you get a material, you get a solid. So in fact, there's a possibility to make artificial Josephson materials by sticking Coulomb islands together. That's from theoretical point of view. from practical point of view, already 25 years ago, there were techniques to put many islands, like several thousands, several 10,000s, simultaneously on two-dimensional plane. Okay, I would not show you 10,000 islands, but to make a structure like this. Periodic system of islands, which are shown with these points, and Josephson junctions, which are shown with crosses. So people become experiments with these arrays. It was very active research topic for more than a decade. It was also sure, and let me stress this point now, as far as models of this arrays are concerned, one can make it very easily from elements which we already have. Josephson junctions, right? We have many arrays. For each for many islands, for each junction we can find a pair of islands. They will have corresponding phase, and there will be energy which will depend on the phase difference between these two islands. There will be also interaction of charges in this island. It could be interaction in the same island, but also interaction of charges at neighboring islands. For instance, here and here, the still electric field coming through capacitances. Right, so in principle, one can have to take this into account, but it all amounts to computing inverse capacitance matrix in the system of these islands. So it was pretty clear how to model the system, and it has the same elements as Josephson junction. It has some typical charging energy and some typical Josephson energy. Fine. What people expected, what was one of the ideas to look at, to realize. Oh, let's see. Let us take an array of these junctions and let us consider as a solid. And let us again look at two limits of large charging energy and large Josephson energy. So if you take large charging energy, what would we have? Then, in order to charge an island, you would have to pay quite some energy, right? And this is, in solid state language, an insulator, or semiconductor with very large gap. One really has to pay energy for having a charge excitation. If you look at opposite limit, there will be good network of Josephson junctions. Everything will be superconducting. So it is no insulator, it's a perfect conductor. What does it mean? Already from these two observations, we understand that some transition should happen at intermediate parameters when Josephson energy matches charging energy. Right, so at the one side of this transition, one quantum variable, charge is well defined. On the other side, phase is well defined. So that's going to be quantum transition where both phases are equally defined. Eventually, people think that high temperature superconductors somehow exemplify this sort of transition. One could think of Josephson junctions. Right, so that was one of the ideas. Another idea comes from what one called topology. So let me consider a limit of well-developed Josephson energy. Then each island can be characterized by a phase. And here I choose to denote this phase by a direction of an arrow. Right. And what I showed this picture, it is the same array of Josephson junctions, but I just concentrate only on this particular blockade, particular cell in this network. Right. And it is called topological excitation, or in simpler words, a vertex. In fact, it's an artificial quantum particle which you make with your own hands by realizing such a system. Let us understand why it is topological. Let's take a blockade and let us go from one island to another island, summing up the angles over this phase differences of the angles along this blockade. All these blockades which are in the figure would have zero total difference. So we turn it and the total phase difference accumulated is zero, except this one. Here we have two vectors turned by 90 degrees. So in fact we have 2 pi difference in if you go along the blockade, right? So we have a special blockade, special configuration of this field, and it cannot disappear, cannot go to ground state where all blockades have zeros. You could move it from one blockade to another blockade, but it's how to say, you cannot destroy undestroyable configuration. And it looks pretty much like a particle conservation. One can do very many things with electron. One cannot destroy an electron unless one has what one needs to destroy an electron.
Positron.
Yes, positron, antiparticle. To destroy this vortex, one would need entire vortex where arrows are joined like this, so it will have -2 pi charge. Right. So that's a very conceptual thing. It's a realization of a new particle from, a simple Lego of Josephson junctions and Coulomb blockade islands. Good. So people also realize these vertices, and if there's quantum mechanics as a finite charging energy, these vertices can jump from blockade to blockade. They really can move as quantum particles got localized. So there is a certain duality between charges and vertices. Both can be particles in this Josephson arrays. Fine, so it was interesting research direction, which unfortunately had to stop due to technological reasons. One can easily make big number of Josephson junctions, put it onto a substrate. One can easily make contacts. What is impossible at the level of modern technology is to make these all junctions equal and to prevent charges in insulating parts of the system, which would work as a disorder for charges in the island. Sure, it's not a realization of a material they have. It's not realization of the solid. In fact, they have realized extremely dirty solids. If one would think of materials, they would mix up all possible chemical elements in one pot. So at the moment, this research direction is almost stopped. So although people keep this technology, they wait for further technological developments. And then hopefully, perhaps you or your generation after you could profit from this interesting physics, realize this phenomenon neatly. Good, that was about homemade quantum mechanics, combination of Josephson effect and Coulomb blockade. Simple quantum systems. Thank you for your attention.